The second topic that we're going to talk about is resonance. So what is resonance? Sometimes if I give you a molecular formula, so if I give you a molecular formula here and I ask you, go ahead and draw the Lewis structure for this molecular formula. One student might draw the Lewis structure like this. Another student can come up with another Lewis structure like that. Which ones are right? Both are right. As you can see, the connectivity is the same. This means that hydrogen is connected to carbon, carbon is connected to the oxygen, same. See, connectivity is the same. Carbon connected to nitrogen, nitrogen connected to hydrogen, everything is the same. So the connectivity of the atoms is the same. This is the definition of resonance. However, the only difference is the arrangement of electrons. How electrons are arranged. Between the carbon and the nitrogen, there is a single bond in one resonance structure or in one Lewis structure. In the second Lewis structure, there is a double bond between the carbon and the nitrogen. And here I do have a double bond between the carbon and the oxygen. Here I have a single bond between the carbon and the oxygen. So see, the electrons basically are delocalizing. Delocalizing is a term that we use for the movement of electrons. So the electrons are delocalizing in this section over here. Everything is the same. It's just the arrangement or the movement of electrons differs from one Lewis structure to the other. So this is called Lewis structure, LS for Lewis structure 1. This is the LS for Lewis structure 2. Which one is the true representation of the Lewis structure? It's actually both of them. So normally we combine both of these structures in one structure, which we're going to call a hybrid. I'll show you how to draw the hybrid once we explain the resonance and the conditions for resonance and the movement of electrons. Okay. So in order to represent two Lewis structures, if you have two Lewis structures, these are called two resonance structures. So if you have a possibility of drawing a certain molecular formula two ways, the connectivity is the same. Everything is the same, but the number or the arrangement of electrons differ. We're going to call those two resonance forms. To represent those resonance forms, we're going to use a double head arrow between them, just to show electrons move from one structure to the other. The true resonance structure is the combination of compound A or Lewis structure A and Lewis structure B, which we're going to call the resonance hybrid. Okay, now normally when electrons delocalize, this means that electrons are spread through a large surface area. When they are spread through a large surface area, this increases the stability of the structure. So molecules with two or more resonance structures, these are called resonance stabilized, because resonance is kind of like the electronic cloud, and if the electronic cloud is spread over a larger surface area, the structure will be more stable. Let's start with the conditions to draw resonance. First of all, you should have, because as I mentioned, resonance structures are Lewis structures. They are just showing different arrangement of atoms, the same connectivity of atoms, different arrangement of electrons, same connectivity of atoms, different arrangement of electrons. So the electrons are different, but the connectivity is the same. Hydrogen connected to carbon, hydrogen is connected to carbon. Carbon connected to oxygen, carbon is connected to oxygen there. So these two, A and B, are basically resonance structures of each other. Drawing a double head arrow between those is a must. This tells me that these two are resonance structures in there. Now, once you draw these two resonance structures, you have to pay attention to one thing. Resonance structures, they share the same charge. So if you start with a charge, all the resonance structures in there should have the same charge. Here I'm starting with a negative charge. It doesn't matter where the negative charge is. It can be on the nitrogen, it can be on the oxygen, but the point is, I'm starting with a negative charge, then the second resonance structure should have a negative charge. all of the resonance structures should have a negative charge. If one of the structures has a zero charge, then this is not a resonance structure. If one of the structures has a positive charge, then it is not a resonance structure. So all resonance structures, they should have the same connectivity of atoms, but different arrangement of electrons. They should show same charges all over. The second rule, they should not have or the number of electrons should always be the same. So I cannot have, for example, here I have a structure C. Structure C has unpaired electrons. Unpaired electrons means one electron. This is what an unpaired electron is. So you have one electron on the oxygen, one electron on the carbon. I don't have this in A and B. A and B having lone pairs as paired. So you cannot have unpaired electrons like that. This is not going to be a valid structure. So the resonance structures, they must have the same number of unpaired electrons. Same number of unpaired electrons. So if you have unpaired electrons, all the resonance structures should have the same number of unpaired electrons though. So C is not a Lewis structure of A and B. And then rule number 3, Lewis structures should be valid. Resonance should have valid Lewis structure. This means that carbons should have how many bonds? 4. Okay, to have a zero charge. Nitrogen should have how many bonds? 3 bonds. And a lone pair to have a zero charge. Here carbon has 5 bonds. Carbon have 5 bonds. This means that it has 10 electrons. This is not a valid Lewis structure, so it can never be a resonance structures for A and B. So as I mentioned, resonance structures are moving electrons. You are moving electrons. So you should show how you are moving electrons. To show how you are moving electrons, you're going to start by using arrows. And there are different types of arrows in organic that normally we use. Let me go ahead over all of them. So the first one is basically the movement of 2 electrons. The movement of 2 electrons is basically a full head arrow like this. This means that I am moving 2 electrons. Moving 2 electrons from here to there. So I'm moving 2 electrons. Like here, I'm taking these 2 electrons and I am moving those 2 electrons. When I am moving those 2 electrons, I'm going to create a bond in here. So now I'm going to have a double bond between the carbon and the carbon. Another representation of moving of electrons is moving 1 electron. Moving 1 electron is represented by a half head arrow. So this represents the movement of 1 electron. This represents the movement of basically 2 electrons. We are not going to deal with the movement of 1 electron now. We are only going to work with the movement of 2 electrons. When drawing resonance structures, since they differ in the number of electrons, you should show how electrons are moving. This is the rule. Electrons move from the more to the less. From the more to the less. If you have lone pairs, you start moving from the lone pairs. So here I have a lone pair. I start moving from the lone pair. When you start moving, you don't stop. You have to continue. Because if you move those 2 electrons here to form a double bond and you stop, this carbon will have 1, 2, 3, 4, and 5 bonds. Not valid Lewis structure. So you have to continue in there. So to continue, this double bond is 2 electrons, right? So I am moving those 2 electrons from the double bond and I am adding them to this carbon. So now this carbon has lone pairs and a negative charge. These two, this is structure C and D. These 2 structures are considered to be resonance structures because the connectivity is the same. They only differ with the movement of electrons and the charges. Notice I started with one resonance structure being a negative charge. The second resonance structure is going to be another negative charge. One carbon has lone pairs. The other carbon should have a lone pair in there. Okay, this is another example. Another example there. Again, start always with the lone pairs. Don't start with the lone pairs of the oxygen, because if you start with the lone pairs of the oxygen, you're going to add these electrons to the bond between the carbon and the oxygen, so the carbon will have 5 bonds instead of 4, not valid Lewis structure. So we're starting with the lone pair, always start from the more to the less, and the movement is always from the lone pair. You're gonna add these electrons between the 2 carbons to make a double bond, and then you have to continue. Because if you stop, the carbon will have 5 bonds. It is not a valid Lewis structure. So to continue, the 2 electrons from this bond are gonna move and add to the oxygen, just to make sure that this oxygen is negative charge, same as this carbon is negative charge. If you start with one resonance structure having a charge, then the other resonance structure should have the same charge. It does not matter where the charge is at. As long as it is the same charge, then it is a valid Lewis structure. This is in case when you have a lone pair and a double bond. Okay? Now, if you have a double bond and a positive charge, remember what I said. We said that positive charges, these are compounds, or these are basically atoms that lack electrons. So if they lack electrons, I cannot start moving electrons from them because they don't have electrons. I have to move electrons towards them. So always resonance, when you have a plus charge, is towards the plus charge, from the more to the less. Know this. Whenever you have a carbon double bond carbon, the carbon double bond carbon has electrons. So you can use the electrons of the double bond to move it around, because the carbon double bond carbon has electrons. To represent a structure that has electrons, we're going to call it a nucleophile. We will be coming later on to this term. So this is a nucleophile in there. It means that it has electrons. So the movement of the electrons is going to go from the double bond towards the positive charge. Not towards the carbon, not on the carbon itself, but between the bonds surrounding the 2 carbons. So see how I moved my electrons? These 2 electrons, they go to form a double bond between the carbon. So now this carbon over here, because it lost electrons, this carbon, it lost electrons. I moved its 2 electrons, so now this carbon is going to be a positive 1 charge. How am I knowing these charges? It's simply from the table, or you can calculate it's a charge. This is why I told you it's a waste of time to do the calculation. I know that carbons, if they have 3 bonds, this is 1, 2, and 3. 1, 2, and 3. So if carbon has 3 bonds, it's basically a positive 1 charge. Okay? Again, if you have, so this is the case where you have a double bond and a plus charge. Another case is when you have a lone pair and a plus charge. Always your movement of electrons is going to be towards the plus charge. From the more to the less. The positive is less. The lone pairs and the double bonds are more. So you use the full head arrow in order to move those 2 electrons. See those 2 electrons? I am moving them to form a double bond in here. So now I'm having oxygen with the 3 bonds and the lone pair, so oxygen is going to carry a positive charge. Okay. Resonance hybrid, it should, resonance hybrid is basically the combination of all of the resonance structures. So sometimes you have 2 resonance structures, sometimes you have 3, 4, 5, 6. It just depends on the molecule there. So you just combine all the resonance structures in there. How you do this? This is the true Lewis structure. It's the combination of all resonance structures. How do you do this? You keep the same connectivity, you guys. Same connectivity. So I'm having my connectivity here. Hydrogen is connected to carbon, is connected to nitrogen, is connected to hydrogen, is connected to oxygen. Good? Okay, now you forget about any double bonds. So if you have any double bonds in there, just forget about them. Don't draw them. Now with respect to the lone pairs, make sure that everything is octet. So this is 1, 2, 3, 4, 5, 6. And this is basically, this is going to be 1, 2 over there. Okay. I'm sorry, you shouldn't have 2 electrons in here, because after all, the double bonds are going to be on this section. See, the double bonds basically, they range from between the carbon, nitrogen, and the oxygen, carbon, nitrogen, and oxygen. So this is where your double bond is. And this is what I am doing. I am moving electrons from the lone pair to the carbon, and then I am moving electrons from the double bond and adding them to the oxygen. So since I am adding, whatever you are adding, you are moving and adding, you do not put it in the hybrid. So in the hybrid over here, what I have is this lone pair. See that lone pair? That lone pair, I didn't touch it. So this lone pair is here. And then I have those two. These are for the original structure. These are the two lone pairs in here. I didn't use them. So these lone pairs, you put the lone pairs that are not involved in resonance. The rest are involved in resonance. You just forget about them. You don't put them. Now, after you do this, then you go ahead and see where the electrons are moving. They are moving between the oxygen, carbon, nitrogen. Between the carbon and the nitrogen, it was in one structure double bond, in another structure it's single bond. So all what you need to do is just to draw a dotted line like this between the carbon and the nitrogen. This means that it was once a single, and then in another structure it's a double. Same thing between the carbon and the oxygen. It was once a single bond, and then in another structure it's a double bond in there. So this is basically the hybrid. All what you need to do is just to draw it in the brackets like this. So you have to put the brackets in here. You have to put the brackets in there. And then now you're going to represent the charge, the total charge of your Lewis structure. The total charge is -1, right? In both, it's going to be -1. But the negative charge is distributed between, or divided between, the nitrogen and the oxygen. So the nitrogen is going to carry a -1/2. It's half of the 1. It's -1/2 because that -1 is distributed over 2 atoms. So this is why half of this -1 is going to be on the oxygen and half of it is going to be on the nitrogen. This in case you want to be detailed. So that is going to be the hybrid, and your total charge here is at the top of the brackets. This is going to be a -1. This is how you represent the hybrid in there. If you don't want to be too much detailed for the charges, then I would use the partial negative. The partial negative tells me that the negative charge is once on the oxygen, and then in another structure it is on the nitrogen. So I'm going to leave it to you. Either you divide that negative charge between the two oxygens and nitrogens, or you just put a partial negative charge in there on each, the oxygen and the nitrogen, whatever you want. Now, when you draw resonance structures, one of them is going to be more stable than the other. The more stable, we're going to call it a major contributor, and the less stable, we're going to call it a minor contributor. Just know that normally electronegative elements prefer to have negative charges. And normally major contributor resonance structures prefer to have fewer charges. So in case you have two resonance structures, like here I am having a resonance structure and another resonance structure. If you move the bond between the carbon and the oxygen, now the carbon will lose electrons, so it will be positive. The oxygen will gain 2 electrons, it will be negative. These two are resonance structures of each other. This is a 0 charge, this is a 0 charge. Remember what I said. When you do resonance structures, the charges has to be the same for every single resonance structure. I didn't violate here the charges, they are the same, because this is a 0 charge and I ended up with having another one 0 charge. But since the second resonance structure has charges, this first resonance structure does not have any charges. Normally the major contributor is the resonance structure with the fewer charges, and I do prefer carbon always to be octet. Here carbon is not octet, so this is why I'm going to call this minor contributor, and this is going to be a major contributor. Okay, another example here, resonance. How am I moving the electrons? As I said before, movement is going to be from the more to the less. You cannot start your resonance from this lone pair because you're going to have 3 bonds over here. Okay, so you're going to have 3 bonds over there, and then you cannot, so if you have 3 bonds over here, you cannot do anything on this bond. You cannot break a single bond. You cannot break a single bond, remember, nor you can move the electrons of the single bond. So this is why I have to start from the oxygen. So starting from the oxygen in there, from the lone pairs of the oxygen, I'm going to move the electrons here to form a double bond. See? So now I'm going to have a double bond between the oxygen and the nitrogen. And then I cannot stop. I cannot stop. Since I moved, I have to move the double bond. If there's an adjacent double bond, I have to move it to add its electrons to the oxygen. Now it's a negative charge. If I stop, then this means that I'm going to get a different charge than my first resonance structure. So they will not be resonance structures, both of them. Now, between those two, the major contributor is basically the structure with no charges, with fewer charges or no charges at all, compared to the to that Lewis structure that has a positive charge on the oxygen and a negative charge on the other oxygen. Just let me clarify one thing, okay? Because some of you will do that mistake. Some of you will do that mistake in here. If I start my resonance structure on this oxygen, so if I do this, okay? If I do this, then my structure is going to look like that. This is going to be my structure in here. Going to have a hydrogen, and then an oxygen. I didn't do anything to this section. This is a nitrogen in there. I didn't do anything here, but I formed basically a, see that triple bond there? You see that a triple bond over here? And you have an oxygen there. You see that? So I'm going to have an oxygen in here. I'm going to have 2 electrons in there. Okay? Well, basically I can move. I can use those lone pairs and form a triple bond. And this lone pair can form a double bond in here. Yeah, let me use that. So this lone pair can form a double bond in here. So let me go ahead and erase this. And basically, just to show you something, okay? So if this lone pair forms a double bond in there, so what's going to happen? This in case you decided that you want to start from here. See how much electrons the nitrogen has. Nitrogen should have a max of 8 electrons. This occupies the octet or follows the octet rule. So nitrogen, to be neutral, it needs to be 3 bonds and a lone pair. This is a 0 charge. Nitrogen can have a max of 4 bonds with a plus charge. See how many bonds my nitrogen has. So there is no way for me I can have this as a valid resonance structure or Lewis structure. This is why you cannot start from the oxygen. You cannot. You have to start from this oxygen. You have to start from that other oxygen in there and move. Always start from the lone pair towards the single bond. That's the easiest. Make sure that your charges remain the same. So if your charges are 0 and 1, they should carry on to be 0 in all the resonance structures there. Okay, this is another example of 2 CH3s connected to a carbon double bond. Oh, this is the Lewis structure for it. Okay, you can draw it in another Lewis structure in there. So moving the electrons, this is how you move the electrons there. I don't have any other way to move electrons across the CH3s. My only movement of electrons is basically between the carbon and the oxygen. I can move the electrons from the double bond to the oxygen. So I am adding a lone pair to the oxygen. So I'm going to have here 3 lone pairs on the oxygen. This is one way. In that case, carbon will lose electrons. It will be positive. Oxygen would gain electrons because I added 2 electrons to it. It will be negative. So this is going to be one resonance structure there. Another resonance structure, I can go and take electrons from the double bond and add them to the carbon. This is less likely to happen. Let me explain why. Carbon is less electronegative than oxygen. So carbon, normally we don't prefer that carbon bears a negative charge. We prefer the negative charge to be exclusive for electronegative elements. So carbon should bear a positive charge, not a negative charge. So this is why that structure is completely unstable, because oxygen is already electronegative. It's already electronegative and already is going to pull electrons towards it. So it doesn't make sense that carbon over here is a negative charge. So this is completely unstable, and normally we don't draw that structure here. Between those two structures, A and B, structure B is going to be the major contributor. Structure A is going to be the minor contributor because of the charges, but notice both are zero charges. Okay, now as I mentioned, if you have a positive charge, your resonance is going to be towards the positive charge. From the double bond towards the positive charge, so I'm taking those two electrons, adding them on the oxygen. So now my oxygen is going to have two lone pairs instead of one. What's going to happen to the carbon? It lost electrons. So now my positive charge is here. I'm starting with one resonance structure being plus here, the other resonance structure being a plus there. Okay, which one is a major contributor? Always try that your major contributor is the structure that basically has its atoms satisfying the octet rule. And here in this case, carbon satisfies the octet rule. Oxygen does satisfy the octet rule, but carbon here is a zero charge. So carbon is a zero formula charge, and it does satisfy the octet rule in there. It does have 4 bonds. So carbon having 4 bonds is more stable than carbon having 3 bonds and the positive charge. So this is why it is a greater resonance contributor. These are 2 examples of resonance structures. So all what I did over here, this is all what I did. You start your resonance from the lone pair, you move it towards the sigma bond. So you create a double bond in here, move on, keep moving, don't stop. If you stop, carbon will have 5 bonds. And then the electrons on the double bond will add to the oxygen, so oxygen will have 3 lone pairs. And now oxygen will have a lot of electrons, so this is why it's a negative charge here. If I want to draw the resonance hybrid, then this is how the resonance hybrid is going to look like. You just draw the same connectivity of atoms that you're seeing. The electrons that you are moving, you neglect them. You just go ahead and neglect them. Any other electrons that are fixed, keep them. So I'm having here these 2 electrons, they are fixed. I didn't do anything to them. I am gonna put them there. I am having a CH3 over here. I'm just gonna go ahead and put it. So this is gonna be my resonance hybrid. Okay, now see those electrons, I am moving them, so I cannot put them right now. This is not right. So now my electrons are moving between the carbon, and the oxygen. So between the carbon, and the oxygen in one resonance structure, it is a single bond. In the other resonance structure, it's a double bond. So all what you need to do is just go ahead and put a dotted line between the carbons, showing that in one resonance structure, it's single, in the other resonance structure, it is a double bond. And same thing for the carbon double bond O. This is basically my dotted line. So my electrons are moving across this area over here between the 2 carbons and the oxygen. Now with respect to the charge, I do have a charge of -1 in there, so it's up to you. You can put either partial negative here, partial negative there, or I'm going to use a different color there, or you can put -½ here and -½ there. Whatever you want, okay? Always make sure that your resonance structure is a valid one. So you cannot do a triple bond in here. You cannot start by moving the lone pairs towards the double bond. This is not true, because you're going to end up basically having carbon with 5 bonds. Your actual resonance structure for this one, draw the double arrow. This is for the representation of the resonance structure. You start from the double bond and move it like this. So your actual structure over here is going to be, this is a CH3, this is a CH3 over there. It's going to be not a double bond. I'm sorry, it's not going to be a double bond in here. So let's go ahead and erase that. And it's going to be a single bond with an oxygen, and it's going to have a lone pair over there. I added electrons to the oxygen, so it's negative. Anyways, oxygen with a single bond, 3 lone pairs, is a -4 mole charge. carbon with 3 bonds, it is a positive charge. So again, zero charge over there. To draw the resonance hybrid for this structure, again, we draw the CH3, we draw the carbon, we draw the oxygen in there, and we draw the CH3. On the oxygen, these two lone pairs, I didn't do anything to them. So these two lone pairs, they stay the same. What actually is changing is basically the double bond in here, because in one structure you have a double bond, in another structure you have a single bond there. And pretty much that's it. This is going to be your resonance hybrid. This is going to be the resonance hybrid. The total charge is a 0. Okay, so this is going to be partial negative. This is going to be partial positive. This is a 0 charge. So you don't have here negative half, negative. You can do -1 + 1 if you want to have a 0 charge. It's up to you. So you can do -1 on the oxygen, you can do +1 on the carbon. This is a 0 charge. Or you can just leave it as a general partial negative, partial positive. Another example, NO2. So my question here, draw the Lewis structure for NO2 negative. So for NO2 negative, there are 2 Lewis structures in there. So you have to draw the resonance structure for NO2 negative. So start by drawing the nitrogen, the oxygens in there. You end up having 1 Lewis structure. And then you can see that this Lewis structure in here can undergo resonance. It can undergo resonance to another Lewis structure. So the lone pairs are going to form a double bond between the nitrogen and the oxygen. The double bond is going to move to form basically an additional lone pair on that oxygen. These two are resonance structures of each other. Make sure that you have the total number of electrons in there. You have 18 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So all what you need to do, again, draw the Lewis structure in one form, and in case you can do resonance, do the resonance to get the other Lewis structure in there. So my resonance hybrid, let's draw the resonance hybrid. I'm having an oxygen and an oxygen in here. This is going to be my resonance hybrid. I have 2 lone pairs that I didn't do anything with on this oxygen, so I'm just going to go ahead and put them. Okay, and I do have 2 lone pairs on this oxygen I didn't do anything with, so I'm just going to go ahead and put those 2 lone pairs in there. And then here you go. So now what I'm going to have is just go ahead and put the charge. I do have a 1 negative charge. This is -1 like this. This is a -1. Now the negative charge is divided between this oxygen and this oxygen. Nothing on the carbon, on the nitrogen. Oh, I forgot the lone pairs on the nitrogen. Let's go ahead and put the lone pairs on the nitrogen. Lone pairs should be on the nitrogen here. 2 electrons on the nitrogen. So the oxygen has a negative charge on 1. So this is going to be -1/2. This oxygen is going to have another negative charge, so it's going to be -1/2 because the -1 is shared between both oxygens. I can do it like this, or as I said last time, you can do partial negative on the oxygen and another partial negative on another oxygen, whatever you want. Acetate ion, this is another example. Ozone is another example. So with ozone over there, you have a 3 × 6. This is 18 valence electrons. So you just go ahead and you draw the Lewis structure for ozone. You don't have any other choice but drawing the oxygens together like that, linked together. And let's start putting the 18 valence electrons. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and see, you have over here 17, 18. But drawing it like this, see, these 2 oxygens are going to be both negative. And see this oxygen over here? We don't have a structure where oxygen has 2 bonds and 1 lone pair. It doesn't exist. Oxygen should have 3 bonds and the lone pair to be a positive charge. So this is an easy fix. I would take one of these lone pairs and I would make a double bond between the 2 oxygens. And I'm going to be ending up having this resonant or Lewis structure in there. Make sure you write your formal charges. Oxygen will be positive, basically this oxygen will be positive, this is going to be a negative charge. I know that ozone is a zero formal charge, so this is why I should have it as a zero charge. This means that if I'm doing a second resonance structure of ozone, it has to be a zero charge. So to do the resonance here, all what you need to do is move the electrons from the oxygen to form a double bond between the two O's, and move this double bond to form a negative charge on this oxygen. Why negative? See those two electrons? I am adding them to this oxygen, so this is going to be a negative charge there. So now my resonance hybrid is going to look like that. This is a total of this is a total of 0. I'm sorry, it shouldn't be a negative there. It should be a 0 charge. You don't have to write 0, but I'm just going to go ahead and write the 0 over there. The double bond can be either between these two oxygens or between these two oxygens there. Just go ahead and put the lone pairs that you did not work with. I didn't work with these two lone pairs, this lone pair and these two lone pairs. Other than that, I moved this lone pair here to form a double bond, so you shouldn't include it, because you're already including it in a form of a double bond there. You can either use partial negative, partial positive, partial negative, partial negative in there. So I'm having partial negative in there, and this is going to be a positive. Pay attention, if you do partials there, if you do partial negative over here, then you would need that oxygen to balance the negative, the partial negative. So that is going to be it's going to be basically partial to positive, just to balance the negative charges. See what I'm saying? To have a total charge of 0. So that guy over here is going to be partial to positive, because the positive charge exists on both of these oxygens at the same time for both resonance structures. If you do negative half, you can keep this as a plus a charge, because negative and negative, this is -1, +1, it's a 0. At the end, everything has to be 0. NO3 negative, you just draw its Lewis structure. By now, you should know how to draw this Lewis structure in there and start moving the electrons. So see, this is the first one that has 3 resonance structures. So you start moving the electrons in there. The lone pairs form a double bond. The double bond forms a negative charge on the oxygen. Okay, notice my total charge for the NO3 is 1 negative. I have 2 negatives and 1 positive. So I have to carry on with 2 negatives and 1 positive so that every single structure has a -1 total charge. Okay, so here I'm going to have a negative charge on this oxygen. Moving this way, lone pairs can form a double bond. This double bond can form a lone pair on the oxygen. Then you're going to have basically a negative charge on this oxygen. So see, I am basically moving my electrons. It's the movement of electrons. Resonance is the movement of electrons. So I am moving electrons so that each of these oxygens will have, at the end, they will have a negative charge. So drawing my resonance hybrid, it's going to look like this. I have a nitrogen, I have an oxygen, I have an oxygen here, and then I have an oxygen there. Let's put this in the brackets like that. And then figure out the electrons that I am working with. I'm working with this electron, so I'm working with this electron here. I am working with this electron there. See this electron here, I'm working with it, so I'm not going to include those. What else I'm working with? Pretty much that's it. So let's see. So I have 2 electrons here, so I'm just going to go ahead and put them. I have 2 electrons there. I'm just going to go ahead and put them. These are the 2 electrons. And here I have 2 electrons. I'm just going to go ahead and put them. The rest of the electrons, I'm using them to move them around for resonance purpose. Now, the double bonds are basically along all of these bonds here, because between the NO, it's once double, then single, here, single, single, double, here, single, double, double. So basically the double is all over the place. So I'm gonna put a dotted line here, dotted line here, dotted line here. So each one of these bonds was either single or a double bond in one of the resonance structures. Now with respect to the charges, I know that my total charge is -1. Okay, so it's going to be -1. Now, this is going to be -1. Now, I know that this nitrogen is positive on all of them. So this is going to be a +1 over here. Okay, so you can do +1 there. And then each of these is going to be partial negative charge. This is one way. Another way, I have basically 2 negatives that are distributed along 3 oxygens. Do you see that? 2 negatives distributed along 3 oxygens. So 2 negative out of 3 oxygens, 2 negative out of 3 oxygens. So I can do -2 over 3 over there, -2 over 3 over there, -2 over 3 over there. Or you can do partial negative, it doesn't matter. But now when I add up all of these +1, I should have a -1 total charge, and this is going to be for the molecule, for the NO3. More examples, more examples. Now here I can move this way between the carbon double bond CO. This is one way. Another way, I can move basically I can move the lone pairs this on this side. So this is another resonance structure over here where I'm going to have the negative charge on this oxygen. So it's going to be either or. Lone pairs can either move this way or they can move the other way and form the second resonance structure in there. The way that I did it is moving the lone pairs, forming a double bond. The double bond forms a negative charge on the oxygen. This is one. Another way is after you do this, you can start all the way from the top and use one of the lone pairs, form a double bond. This double bond forms another double bond between the 2 carbons, and then you will form a negative charge on the oxygen. You can do this, or if you want, you can start again from this one, do a double arrow, but now start from this side. Starting from this side, let's use another pen. So starting from this side now, the lone pair is going to form a double bond, and this double bond is going to form a negative charge in there. So now my structure is going to look like this. This is a double bond O. This is a CH3. And then I'm having a double bond in there. Let me show you the carbon, because we did not yet talk about the skeletal structure. So we're still having the carbon here. This is the double bond, carbon double bond. Now this is the C, and this is basically the O, and the O is going to be a negative charge because I added 2 electrons to the oxygen. See those electrons of the double bond? These are added to the oxygen. And I have my CH3 over here. And of course, don't forget this hydrogen. This is another resonance structure. So you can go either by starting from this one, you can form the second resonance structure, or starting from this again, you can form the second resonance structure, wherever you want. Now, with respect to the resonance hybrid, let's go ahead and draw that. It's more practice for you. So this is going to be a CH3. Draw all the atoms and the connectivity of atoms, not the double bonds. So we're not drawing the double bonds in there, just the single bonds. So I'm having the oxygen there. I didn't do anything to these 2 electrons, to these 2 lone pairs. And then I'm having a carbon, and then I'm having a carbon, and then I'm having an oxygen there. Again, I have only 2 lone pairs that I did not work with. And then I'm having a CH3, and of course I'm having a hydrogen. This is going to be my hybrid. My total charge is -1. Right? And where is my double bond? See my double bond? My double bond goes all over this area, all over this area. See, this is the delocalization. And the greater the area where electrons delocalize or electron move, the more stable is the structure. So the structure is really very stable because the area where electrons cover is basically the oxygens and the 2 oxygens and the 3 carbons. So now my double bond is going to be here, it's going to be here, it's going to be here, and it's going to be here. So the electrons move across all of this area over there. This is going to be -1/2. This is going to be -1/2, or you can do partial negative in there, so or partial negative, or partial negative on the oxygen. Oh, I forgot the carbon though. I forgot the carbon though. So basically it's not negative half. I am sorry. See, that negative charge is divided between oxygens, two oxygens and a carbon, right? Between two oxygens and the carbon. So instead of negative half, it's going to be negative 1/3 because it is divided between two oxygens and one carbon, 3 atoms. This is my 3 atoms in there. So I have -1 that is divided over 3 atoms. Does that make sense? It's going to be -1/3, -1/3, and then -1/3 over here. Okay? With respect to the this structure there, we call this allylic cation. Again, I am saying these names, all of these names in there. I'm gonna keep repeating them because once we reach them, we would need to know them. What is an allyl group? An allyl group is basically a carbon that is connected to a double bond. So this carbon is called an allylic carbon. If the carbon has a positive charge on it, it's called allylic cation. Cation is positive. If it has a negative charge on it, then it's called allylic anion. Okay, point is here, I want to know the resonance structure for this compound. So all what you need to do is simply, since this is positive, it doesn't have electrons, I cannot start my arrow from it. I need to start my arrow towards it. So double bonds have electrons, so my arrow is going to start from the double bond towards the single bond here. So now this carbon is going to bear a positive charge, starting with 1 charge. The second resonance structure should bear the same charge there. Okay, so these are the resonance structures over here. Let's draw the resonance hybrid then. So the resonance hybrid is going to be a CH2. Okay, it's going to be a single, so always draw single bonds. Always draw single bonds in there. This is going to be the single bond. And then between those two carbons, it's a double bond here, a single bond there, so draw a dotted line. Single bond here, double bond there, so draw another dotted line. The structure has a positive 1 charge. The positive 1 is divided between this carbon and this carbon. So this carbon, this one. This carbon, between this carbon and this carbon over here. So it's going to be either positive, this is going to be positive half, this is going to be positive half over there to make a total charge of positive 1, or you can do partial positive on that carbon and partial positive on the other carbon, whatever you want to do. Okay. Benzene. Benzene is a cyclic structure which is made up of 6 carbons and 3 double bonds. This is what benzene is. Benzene undergoes resonance. Now with benzene, you do have an electronic cloud above the ring, as you can see that red area in the electronic map. The red area indicates that basically it's rich in electrons. So the electronic cloud around the benzene is above the ring and under the ring. The electronic cloud in there, and benzene is very stable, and the reason why it's stable because benzene undergoes resonance, and the resonance is basically as such: from the double bond to the single bond, from the double bond to the single bond, from the double bond to the single bond. So you end up having this second resonance structure over there. The resonance, the true Lewis structure for benzene is the hybrid. Okay, it's the hybrid in there, and for the hybrid I'm having an alternation between a double, single, right? The double in this structure is a single in that structure, and the double in this structure is a single in that structure in there. So my double bonds are all over the place. So this means that my double bond, to represent it, I'm just gonna draw a dotted circle in the benzene, and this is the hybrid for the benzene. I don't have charges, I just have hybrid. This is why for benzene, you normally, when you draw benzene, the true resonance structure or the true Lewis structure for benzene looks like this. with a sharp circle like that, indicating that the double bonds can be anywhere in the benzene. These are more examples that you can go ahead and work with a solution. Just drawing the curved arrows in there to show the second resonance structure. The point is always start from the more to the less, from the more to the less, always. And once you start, you have to keep moving on your electrons. So start with these electrons and keep going on. Another example, draw the resonance hybrid for the following. So these two are resonance structures. I want to draw the resonance hybrid. So to draw the resonance hybrid, as we said, simply you have the hydrogen over here, okay? You have your nitrogen there, you have a hydrogen. Don't include the lone pairs because the lone pairs you are moving them. And then my CH3, good, okay. Both, they have +1 charge, so this is +1. Now my double bond is between carbon and nitrogen, so basically your double bond is here between the carbon and the nitrogen. That's it. Now this carbon is going to be +½ and the nitrogen is going to be +½ or you can do partial positive for the carbon, partial positive for the nitrogen, whatever you want. For this structure, the resonance hybrid is going to look like this. This is going to be a carbon with a hydrogen, and then another carbon with the hydrogen and the hydrogen. Again, I don't include the lone pair because I am moving them in resonance. So lone pairs and double bonds don't include everything else. My total charge is -1. And the negative is divided between this carbon and this carbon. So basically between these two carbons in there, it's going to be -½ over here. And then you should put where your double bonds are. So the area where electrons are delocalized, they are moved, are between the carbons, the 3 carbons in there. So this is going to be my area in here where you have a double bond. In this resonance structure, you have a single bond in that other resonance structures, and then it alternates. So this is going to be the hybrid. You can follow the question and the solution for this problem in the same way.